understanding, we need a robot with 5 degrees of freedom to solve the problem. We don't need 6 degrees of freedom robot. So our robot arm is, let's say, like 5R, just as an example. It doesn't have to be any 5 joints. So in that case, the number of inverse kinematic solutions is discrete. Question number 1, it's a series of questions. We are looking for research partners. Parentheses, we're working on it for already 2 years, stuck on it. We need somebody to get us out of the local minimum. Question number 1, what is the number of inverse kinematic solution for this problem? It is known that for 6R robot, complete position and orientation, there are at most 16 solutions. So let me repeat it. We have 6R robot. I specify 6 end conditions. The well-known result is that it is a tight lower bound. There are 6 examples in which the number of solutions to the inverse kinematics is 16. What's the bound on the 5R robot? What's the number of solutions, lower bound? So question number 1, number of solutions. Question number 2, this is how we are going to plan to attack this problem in general. We think about the workspace of a 2 revolute joint robot. Did you ever realize it's a torus? Let me show you what I mean by that. Sorry. Okay, so I don't want it to break. I'm in teaching mechanical engineering. I better strengthen some stuff here. So the idea is, look, the workspace is generated by 2 circles. I have now a gripper which sits maybe right here. But there's no joint here. So when I rotate the joint theta 2, I get a circle. Okay, this is part of the workspace of the robot. Now I take this circle and rotate it about theta 1. I get a torus. It's called the general torus. Let me take the circle and rotate it about the z-axis. So you get something which is roughly, something like this. And that's the workspace. Okay? I'm saying an important sentence. If the 2 axes are orthogonal, mutually orthogonal, it's called the right torus. But in general, and for robot arms, this is not a right torus, but just a general torus, 2 generating circles. So I'm arriving to the main question. If we have 2 such robot arms, each one is only 2 joints. RR robot looking at another RR robot, and they just want to handshake the grippers. We want the center of the grippers to reach a common point. Geometrically, the problem is take 2 tori in space, intersect them. We have an assumption, we are not able to prove it. The number of intersection curves of 2 tori is at most 4. Okay, and this is my big question. How do I erase this stuff here except with my hand? Is any? Oh, thank you very much. Question 2. Any other pen? Here it is. Question number 2. That's the central question. T2 cross T2 at 4 curve. Yeah, I can give you some ammunition. If you look at the top view of a torus, okay, top view, the number of intersection points of an ellipse with the toes, if I understand it correctly, I just did it like 2 minutes ago, it seems to be 8 points. I think I'm correct. Steve, you watch my back. 1, 2, 3, 4. 1, 2, 3, 4. 8 points, okay? But, so we were able to prove the following fact. If you take a toes, a two-dimensional toes, a general toes or right toes, intersect it with a circle, not an ellipse, 4 points. Okay, so we proved it algebraically. So if you take a toes, intersect it with a circle, try me, maybe here. It's a circle, it's not an ellipse. 1, 2, 3, 4. So we can share with you the algebraic proof that the intersection of a circle with the toes at most 4 points. The question is, how can we show using any approach algebraic? Look, hand waving, we're almost sure the assumption is correct, at most 4 curves. We want a proof, algebraic proof, why it is at most 4 curves. We're working on it for 2 years, stuck. Let me show you, it's really interesting to know it was solved for the right toes problem by a Korean PhD student. He did the following amazing thing. He said, if the toes is a right toes, remember the 2 axes are orthogonal, the right toes can be generated by rotating a sphere about a circle. So the sphere is like the inner sphere, you rotate it, you generate the toes. So he said, let me build the configuration space of one of the 2 right tori by shrinking this sphere to the point and expanding it. So remember, the sphere like now has to touch the toes. So the configuration space, I can shrink the sphere to a point. And I'm getting a little lost here because I'm supposed to get 2 tori as a result. One is outward. The inner one, I lost it, but they're supposed to be the boundaries of a configuration space obstacle. So I converted it like to a motion planning problem with configuration spaces. So one of the tori was shrunk to a circle. It's a generating sphere. He pressed it into a point, and somehow generated like an outer toes and an inner toes, which I'm missing the inner toes. And then because it was shrunk to a circle, the other toes we didn't touch. It reduces to the problem of intersecting a circle with the toes, and he has like an inner toes. Again, I lost the inner toes where it is. Outer toes get at most 8 points. You can pair them and get 4 curves. So let me just repeat the question. Not right tori. For right tori, we know a general toes that I just plotted cannot be generated by rotating a sphere inside. There's no way. The cross-section is really thick. And let me just finish this open problem by saying where we are heading with it, why we are interested in this problem, because we said we are going to solve the inverse kinematics problem by actually allowing breaking our 5 degrees of freedom chain into 2 robots. So we have like 5R. So we take R, 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 R. So this one, let me just put it like this. It is based to the ground. This is where I have my gripper sitting right here. So our approach is we cancel out the middle joint. We have an RR chain based to the ground. We have an R, so this is like an RR chain to the desired position in 2 degrees of freedom of orientation. Okay, so now what is happening, we are going to replace this joint by a spherical joint. Do you know what is a spherical joint? It has 3 degrees of freedom. There are some mechanical engineers here, 3 degrees of freedom. So total number of degrees of freedom is 1 plus 1 plus 3 plus 1 plus 1 equal 7. By fixing the gripper, fixing the gripper, we actually locked all 6 degrees of freedom. So I remove 6, I get 1. So the closed chain, RRSRR, is a 1 degree of freedom chain. Now, if we break the spherical joint, here's what we have. We have 2 RR robots. Each one has a tori workspace. All the points where the center of the spherical joint can match are exactly the intersection curves of the 2 tori. So in theory of mechanisms, people are asking, give me a closed chain of 1 degree of freedom in 3D. What are the number of assembly modes? This is how they call it. It's an open problem. Does a closed chain with 1 degree of freedom, there are whole papers with catalogs, all 1 degree of freedom closed chain in 3D. But nobody knows whether, and the assumption is they have at most 4 assembly modes. So it has 1 degree of freedom, so it can live along 4 curves in space, this closed chain. Once we solve this problem, here's our trick. If we know that this chain is 4 curves, in order to solve the inverse kinematics problem, it reduces to solving the inverse kinematics problem on those 4 curves. On a curve, you can do a optimization like gradient descent, checking all the local minimum. You can define a cost function. When the cost function is 0, you get exact matching of the original 5R chain. So let me just go back down to the ground level. So there's all this machinery hiding inside. 2 tori, not right tori, 2 tori, help us prove that they intersect at most at 4 curves. Or save us our precious time, give us counterexample. There are more than 4 intersection curves. Please.
Okay, excellent. I think that we have time for about three comments and questions here. But this is a very interesting topological question and well within the meat of the WAFR conference.
Hopefully. Can you put off, Tobias, take off the mask for a second?
No, just to understand the problem formulation, if you intersect the torus with itself, you get infinitely many curves, right?
Oh, you have two different tori.
Assumed to be different. What are the other assumptions? Same size. And...
So you have 2 different robot arms. Each one is 2 degrees of freedom.
Mm-hmm.
And the workspace of each robot arm, if you look at the center of the gripper, is a 2-dimensional torus. It's a surface.
Okay, and they have the same sizes?
No, they're completely general. No, they have different sizes and different
center.
Angle between the joint axes.
Okay.
So there are 2 general tori. Forget about the robots. Just give us the intersection of the 2 tori. At most 4 curves.
Okay, thank you. I would need to think about it. But just to
and no
take out the trivial solution.
Not just the fished algorithm to compute it. Bounds, hard bounds.
Okay, thank you.
Okay, we're going to ask 2 more questions.
So for your first question on computing the number of solutions in the inverse kinematics problem, don't you just need to compute the mixed volume of the system of equations that you have?
Compute what? I missed
the mixed volume of the Newton polytope of the variety that you've described.
So maybe you can explain it. I know there are algebraic techniques to solve the inverse kinematics problem of 6R robot. I think it's an eigenvalue problem.
So
it's like 16 by 16 matrix. But you're telling me that what the bound on the 6R robot implies also the bound on our problem?
So you have an inverse kinematics problem.
Yeah, the usual one, the classical one.
Just a classical inverse kinematics problem, and which you can rewrite as a system of polynomial equations, right?
Yes, correct.
And then you want to count the number of solutions to the system of polynomial equations?
Yes, but now I have only 5 degrees of freedom and only 5 conditions.
But it's still you want to count either the dimension of the solution space or the number of solutions.
Yes, and
so
do you have any insight? You think
there's like a classical problem in algebraic geometry where you either want to compute the dimension of the variety or you want to compute the mixed volume of the system of equations of the Newton polytope.
So you're saying, because I never studied these tools, so you have a method to actually compute at least a lower bound, or We need a lower bound on the number of solutions. So you think this is the right way to get it?
Yes.
Perfect. So can you chat a little? Thank you very much.
Yes, I think this is good. Do we have one more question? Anybody?